Can you all see the slides?
Yes.
Yes.
Perfect.
Yes.
Okay. So, well, thank you very much for the invitation to talk here. I'm going to talk about the classification of groups of finite type by isomorphism. So this is going to be about groups acting on trees. So let's start talking about what binary tree and ternary tree, what trees are. We are going to have a root, a special vertex, and then we have infinitely many vertices, and they're all going to have the same amount of children. So, for example, in the case on the left, they all have two children. In the other case, they all have three children. This is somehow like a picture with high quality. So I'm referring to YouTube. That you can probably see, like when you have a video, you have like 1080 pixels. Like the bad quality picture looks more or less like this. That is on the right, where it's a bad quality picture, so we don't see the vertices that are inside, but the vertices are there. So I'm gonna use this bad quality picture because it is enough for the purpose of my talk. But this triangle here represents the trees that are above, just in bad quality. So OT is the group of automorphisms of the tree. So are the elements that act on the tree preserving adjacency. OT is a topological group. And since the elements in OT preserve adjacency, they also act in a truncated tree. If you just cut and look at the first n levels, it acts in that truncated tree. And T to the n is going to be the notation I'm going to use. If V is a vertex in the infinite tree, T sub V is going to denote the subtree that has V as a root. So in the bad quality picture, again, you can see we have a vertex V somewhere there. And the vertices in T sub V are going to be the vertices that are grandchildren of V. If G is an automorphism of the whole tree by preservation of adjacency, if we restrict the action of G to T sub V, it has to send T sub V to T of G sub V. And since all these three are basically the same, they look the same, we can identify these subtrees with the original infinite tree and see this restriction G restricted to T sub V as an element in OT. For short, we are going to write G sub V instead of G slash TV. And this is called the section of G at V, and basically it's telling us how G acts on the subtree below V. Okay. And then we can truncate the action to the first n levels below V, and then we're going to have what is denoted here as G sub V to the n, that is the action of G on the first n levels below V. And this is going to be an element acting in the truncated tree with n levels. Okay, so now what if we choose a tree which is a number D and which is a subgroup acting in the truncated tree with D levels, and we work with the elements in the infinite tree that when we restrict the action to the first D levels below any vertex V, they act as something that is in this chosen subgroup. If we do that, what we obtain is a closed group of OT that is a group of finite type. That is also known as finally constrained group. Maybe that's another name that you have heard. These are two different names for the same thing. And these groups are denoted G sub P because they depend on the subgroup P we chose at the beginning. So basically, we are forcing the local actions, the actions below V in the first D levels below V at any vertex V to be in a certain subgroup that we chose, this subgroup P. This subgroup is called the subgroup of allowed patterns because those are the actions that are allowed to use locally. And the number D is called the def. These groups were introduced in 2005 by Grigor Shuk, and they have been broadly studied in these 20 years. I put 3 references that are at the end. And the people have studied their Hausdorff dimension and when they are topologically finitely generated in particular. But the question, and some examples, for example, if we choose the subgroup of patterns to be, the allowed patterns to be P equals 1, basically the only local action that we allow here is to act like the identity. And so at the end, the only element that we can create is the identity element, and GP is going to be the trivial group. Another example, for example, if we choose P to be all the automorphisms in the truncated tree with D levels. Basically, we are allowing any local action to appear, and at the end, we're going to obtain the whole group of automorphisms of the tree. So these are kind of like two trivial examples of groups of finite type. Something in the middle, if we choose the depth to be 1, so we are imposing an action in the children of any vertex. So the subgroup P is going to be something in the symmetric group of D elements because we have D children at any vertex. And at the end, what we're going to obtain is the iterative Ritz product of this subgroup P we choose. And then more examples appear when Sunich proved in 2006 that the closure of regular branch groups are groups of finite type. And so now we have examples like the first Grigor group and the closure of the first Grigor group, the GGS groups, the iterative monochrome group of C squared plus I, etc. These groups of finite type are self-similar. They are branch, and moreover, they are regular branch. That is like a particular family of branch groups. Okay, so now the question of this topic, the question of this talk is, if we have two groups of finite type acting on the same tree, is there an easy way to know if these groups are isomorphic as topological groups? So isomorphism of groups, and that is also homeomorphism. Okay, why is this question important? Well, first of all, it's always interesting to classify things in mathematics. But if that's not enough, I have two other reasons to study this. So imagine we have two abstract groups in OT, and such that their profinite completions are isomorphic to the closures of G1 and G2 in OT. This is not something crazy to think about because there are so many examples of groups whose profinite completion coincide with the closure in OT. The first Grigor group is an example. GGX groups satisfy that, and the third Grigor group also satisfies that. And there are like a bunch of articles of people studying when this is true, when it is not. So let's take one step more, and let's imagine that this closure in OT is a group of finite type. For example, if the group's a regular branch, we know that's true. And then if I have time, I'm going to show you a slide that gives more results in that direction. Okay, so if we have that the closures are not isomorphic, that implies, because they're assuming that they're profinite completions, so the profinite completions are not isomorphic. So in particular, the groups, the abstract groups we started with are not isomorphic. But on the other hand, the closures are isomorphic, so the profinite completions are isomorphic. And if we somehow find another way to prove that the groups are not isomorphic, that implies that the groups are not profinite rigid. So even proving that the closures are or are not isomorphic, we still obtain information that is valuable. So these are two other motivations to study this. So the first thing I'm going to do is we may assume that the subgroup of patterns have the same depth. At the beginning, we have two groups of finite type. They can have different depths, but we can enlarge somehow the allowed patterns, and we can definitely assume that the depth is the same. So from now on, I'm going to assume that. And the first case that one can have is if we have two groups of finite type GP and GQ, they are isomorphic if and only if the subgroup of allowed patterns are isomorphic. However, this is not true, and I'm gonna show an example at the end. So the first thing that we can try is using conjugations. So in OT, so we take G and element in OT, we have conjugations in OT. As if we want it to be an isomorphism between GP and GQ, what we want is that phi of GP is inside GQ, and phi minus 1 sends GQ to GP. If we impose that, we obtain two conditions over the conjugator G. There are that for every vertex, the local action of G at any vertex has to conjugate P onto Q. And a second condition that says that for every pair of vertices in the same level, the local actions are equivalent modulo Q. For that reason, I decided to define this set that is basically all the possible local actions that conjugate P into Q. That's basically based on the first point. And then an equivalence relation in this set that is that two local actions are equivalent if and only if they are equivalent modulo Q, basically because of the second condition that appears. However, this is not enough. because we can have the local actions satisfying this, but then we need to glue them together in order to generate an element G that acts in the whole tree. So you can see the picture here. Here we can have like a local action below V, and then we can have a local action below a child of V, and they overlap, and the actions that overlap have to match. And in the two conditions we have so far, we didn't impose that. So we need to add another condition in order to glue the patterns together in order to make a whole element. So for that, I define this direct graph that the vertices are the classes of the set that I just mentioned. And one class is connected to another class. Basically, if for any element in my class C, I can find the patterns, the local actions in C prime that extend my element R at any children of, at any children. And when we do that, we obtain this result that says that if this directed graph has a cycle, then GP and GQ are isomorphic via conjugation. And what is interesting is that the converse is not really far to be true, because if the group is fractal, it is an if and only if. Fractal is the same of recurrent or self-replicating. The same concept has different names depending on the author. So maybe if you know one of these names, I'm talking about the same. Okay, so that's about isomorphisms using conjugations. So what about the general case, if you don't have conjugations? It's very hard to like be able to imagine all the isomorphisms that we can have. So maybe a better strategy here is like, instead of studying all possible isomorphisms, let's try to prove that conjugations are the only possible isomorphism. That's a property called rigidity. And in fact, I have a result in that direction that says that if the groups of finite type are super strongly fractal, then the isomorphism can only be conjugation, and if and only, so that implies that they are isomorphic if and only if there is a cycle by the previous analysis. Super strongly fractal is a more restrictive condition, so it implies fractal. It is not a crazy condition. All the groups that I mentioned at the beginning, they all are super strongly fractal, for example. Okay, what do we obtain with this classification? For example, the binary tree with def2, it was calculated by Bondarenko and Samoilovich 10 years ago that there are 6 groups of finite type. 3 of them are finite, but there are 2 isomorphic classes, and the other 3 are not isomorphic, basically by using the main result. In total, we have 5 isomorphic classes. Binary tree, but with def3, there are 60 groups, 23 are finite, and they split in 4 classes, and the other 37 split in 19 classes, so we have 23 in total. In def4, we have 4,544. This was also calculated by Bondarenko and Samoilovich. 32 of them are infinite and topologically finite generated. That was also calculated by them. These 32 groups are super strongly fractal, so we can use the main result, and we obtain that there are 8 isomorphic classes. In this family of def4 groups, we find, for example, the closure of the Grigor-Schuh group, the twin of the Grigor-Schuh group, and they have the same closure, by the way. And then we also find the Tenei-Moderomi group of C squared plus I, and the third Grigor-Schuh group that they don't have the same closure, but the closures are isomorphic. We have the directed graph here. We can see that there are 3 cycles. In particular, there is 1. Then in the ternary tree, we have in def2, 588 groups of finite type. 166 of them are finite, but they split in 4 isomorphic classes, and the other 422 split in at most 36 classes, but no less than 19. I cannot completely classify here because there are so many groups that are not even fractal. And that's the reason I could just give an lower and upper bound. And in def3, are just restricted to infinite Pro3 groups, and there are 44,671 groups, but only 216 of them are topologically finitely generated. They are all super strongly fractal, so we can apply the main theorem and we obtain 12 isomorphic classes. But if we look at this subgroup of allowed patterns, there are 6 classes, which means that we have allowed patterns that are isomorphic, but their associated groups of finite type are not isomorphic. And I have an example of a graph here, where you can see that there are vertices, which means that the subgroups of allowed patterns are isomorphic, but there is no cycle. So the groups of finite type are not isomorphic. Okay. Definitely, I don't have time to show you this slide. So I'm just gonna go to the references. Bondarenko Samulovich, I mentioned it many times. Then one article talking about Hausdorff dimension. This is the article that Sunich proved what I mentioned before. And the last one is where all these things that I said are or are going to be because I plan to put this in archive soon. Well, thank you very much.
Thank you very much.